Hi, let us continue with the design example related to reinforced concrete peg footing. So far, we have done 3 examples for the peg footing subjected to various types of loads. We did an example regarding the peg footing subjected to axial loads. Another example with the axial load plus the moment in the major axis. And then the peg footing subjected to axial load plus the moment acting in the minor axis. Now we're going to try another example. This time we are dealing with the axial load plus the moment acting in both axes. By going through these examples, you can see the differences in terms of the calculation steps, designing a reinforced concrete peg footing under various circumstances. We will use the same specifications and the load conditions so that you see the differences in terms of the calculations as compared to the other cases. Without further ado, let us get started. First, let us talk about the design specifications. The exposure class is XD2. Assuming the peg footing is subjected to chloride attack and it is always wet. The design life is 50 years. FCK equals to 30 Newton per mm square, which is the lowest grade for the concrete for the applications of the foundations. Using FCK less than 30 is not recommended as far as the peg footing is concerned. Then the unit weight of the concrete 25 kN per meter cube. Steel strength 500 Newton per mm square. Soil bearing capacity 200 kN per meter square. Maximum aggregate size 20 mm. We are using the same column size 300 times 150. The ultimate axial loads 1000 kN, and we have moment in both axes 150 and 150 for the major and the minor axis. Take the reinforcement bar of 12 mm diameter in both directions. First, we need to determine the concrete cover. The nominal cover is governed by C mean plus the deviations. The deviations is 10 mm. And the C mean is governed by 3 factors. First is about the diameter of the steel bar. Second is the C mean due to the durability. This you may refer to table 4.4n in Eurocode 2. By default, the structural class is S4. Under the exposure class of XD2, the C mean durability is equals to 40 mm. The proposed C means cannot be less than 10 mm. We are taking a larger value of the 3 that give you the C mean equals to 40 mm. Plus 10 mm deviations, your nominal cover will be equals to 50 mm. Next, we need to determine an appropriate size for the peg footing. Based on the prescriptive method, the estimations of the size of the peg footing shall based on the serviceability limit state. The questions give the loading in the ultimate limit state. We will need to convert this ultimate limit state into serviceability limit state. This is done by dividing the ultimate load with the factor of safety of 1.4 when we do not know how much is the GK and how much is the QK. This leads to you the axial loads equals to 714.3 kN and the moment equals to 107.1 kN meter in both axes. We do a quick estimations in terms of the minimum area of contact between the peg footing and the soil. This is calculated on the basis of the axial load plus 10% of its load divided by the soil bearing capacity. The axial load is 714.3 kN plus 10% of the axial load, which is 71.4 kN, divided by the soil bearing capacity, which is equals to 200 kN per meter square. This shall serve as a guide for us to propose the dimensions for the peg footing. We know that at least the contact surface area need to be greater than this. However, this estimations is not accurate. This is because the effects of the moment to the soil pressure has not been considered. Knowing that there's going to be influence of the moment onto the soil pressure, when you propose the dimensions, the H and the B, make sure they are slightly higher than this. Since we have the moment acting in both axes of the same magnitude, maybe we can consider providing a square peg footing. When the peg footing is of square shape, the minor axis is likely to be more critical in various aspects, such as in terms of the moment resistance, as well as in terms of the shear load, due to the smaller effective depth. We will come back to this in terms of which axis will be more critical. Let us proceed first. You may propose a thickness for the peg footing. You might need to do some trial and errors until all the shear resistance passed. Previously, for various examples of the peg footing, all the while we have been using the thickness of the peg footing equals to 550. However, in this case, if we use the same thickness, later you will find that the punching shear at the perimeter of 2D from the column face shall fail. That means 550 mm thickness of the peg footing for this particular dimensions of the peg footing, which is 2.4 times 2.4 contact area, is insufficient. Therefore, maybe we just increase a bit into the thickness of 575. This can lead to a slim pass in terms of the punching shear at the perimeter of 2D. We shall talk about the punching shear later in the following videos. Now let us just confirm the size of 2.4 times 2.4 times 0.575 mm. Then we will proceed checking with the soil pressure at the service state. Having the dimensions confirmed, we are able to determine the self-weight of the peg footing. This is calculated by taking the volume of the peg footing multiply with the unit weight. The unit weight of the concrete is equals to 25 kN per meter cube. That gives you the self-weight equals to 82.8 kN. And then we need to determine the soil pressure. This is done by using this formula, taking into the considerations about the influence of the moment. We have the axial load at the supervisory limit state that we have calculated earlier on equals to 714.3 kN plus the self-weight of the peg footing, which is equals to 82.8 kN, divided by the area in contact with the soil, which is calculated by multiplying 2.4 with 2.4. And then we have the moment. Moment at the supervisory limit states equals to 107.1 kN in both axes. Now we need to get the y. Y represents the central axis where the moment rotations happens. This is calculated by dividing the dimensions of the column by 2. Since we are talking about a square peg footing, the width is 2.4 meter at both sides. Divided by 2, you get y equals to 1.2 meter. And then we need to get the moment of inertia in both axes. Again, it is a square section. The B equals to h. You don't have issue with the confusions between B and h. Theoretically, when you're computing the moment of inertia, you will need to sketch the diagram. Now, if this is the major axis, the moment in the major axis is this. The h, it will be the part parallel to the moment. To determine moment of inertia, you will use B multiply h power of 3 divided by 12. And then when you are doing the moment of inertia in the minor axis, you have moment on this side. Now your B become this dimension. B multiply h power of 3 divided by 12. When the section is square, both will have the same moment of inertia. Next is for you to determine the surface soil pressure. Substitute all the value into the equations. You get the soil pressure here. P max represent the larger soil pressure against the moment acting onto the peg footing. And then P min represent the smaller soil pressure due to the uplifting effects as a result of the moment. You may look into the soil pressure, check against the soil bearing capacity, which in this case is 200 kN per meter square. The soil pressure here is less than the soil bearing capacity. Therefore, you will know that the proposed size, specifically in terms of the B and H of the peg footing, is adequate, and you have no issue about the settlement of the peg footing, as you have higher bearing capacity than the stress exerted into the soil.